Let's look for the vertex of a parabola. Finding the vertex of a parabola is a good way to discover the maximum or minimum value that the function the parabola represents will ever take on. And then you can take that idea of minimum and maximum and extend it to more complicated functions. The gold standard for the equation of a parabola looks like this. And if our parabola's expression looks like this, the vertex is at the coordinates given by those two constants, h and k. Our parabola, sadly, does not look like this. We have a generic quadratic expression. We would like something with a perfect square in it. If only there was a way to take a generic quadratic expression and, say, complete part of it to introduce a perfect square. Oh man, that would be awesome. Oh wait, there is such a thing. Aha! Completing the square. So first of all, let's factor the 2 off of those front two terms. We can't factor it off the third term, so let's not. And so already I'm kind of setting up that, see, I even jumped the gun when I wrote that recipe. Look at that, because that's not supposed to be a 2. That's supposed to be just a generic constant a, which is the little tuning dial for how steep or how short and fat the parabola is. And this is also the constant that distinguishes parabolas that open up, positive a, versus parabolas that open downwards, negative a. So I was already planning ahead. But by factoring off this 2, see what I've done. I'm planning ahead for this particular structure. However, I have to improve this x squared plus 6x to make it a perfect square. But we know how to do that. I'm just going to make some extra space. Like so. And then I'm going to remember how to complete the square. And that trick, it's not a trick, it's a strategy, is to go look at this 6, this middle constant on the linear term, divide it by 2 to get a 3, and then square that number, put the result in place here. So go to 6, take half of it, 3, square that, 9, and then add that 9 right on the end of it. Now, we've thrown our equation out of balance, because note that in this whole equation, we've now added a 9 here, but that 9 is also multiplied by this 2. So we've thrown this equation off by a matter of 18, which means somewhere else we have to account for that by taking it away again. And so we can just do that on the outside. It doesn't matter where you do that credit and debit business. When you add things into an equation, just make sure you do it right. The choice of 3, which we then squared, also dictated the form of the perfect square that is the result. That's the genius of that method. And so our parabola looks like this when it's put into what we would call standard form. And so now let's match and find h and k. Now be careful. The standard template wants x minus h. Ours has x plus 3. So our h is negative 3, right? Because we would need to write this as x minus negative 3 if we wanted it to match x minus h. K is easy. That's just the trailing constant, and that's the plus 1. And so our vertex is at the point negative 3, 1. Now, this ability to locate maximums or minimums of a function that's more complicated than just a straight line is crucial in answering more complicated questions, like the one that's posed here. So we have 180 yards of fencing. We're going to fence off a rectangular plot against a stone wall, which means there's no fence here. This is a wall. The fence is this part. It's going to be a rectangle, and we want to know what dimensions of the rectangle will maximize the area. Well, if we're talking about a rectangle and its dimensions, maybe we'd better put some letters on this thing. And let's call this x and call this y, because it's a rectangle and we don't know the length or the width. And if this side is y, then that side is y too. we're trying to maximize the area. Now, I don't know about you, but I can remember how to write down an expression for the area of a rectangle. Based on the numbers that we have, it's x times y. Now, is this a parabola? Well, no, or at least not yet. The problem here is we don't know how to proceed because we have 3 variables instead of 2. So we would like to eliminate one of these variables and write it in terms of the other one. And so we have to think, is there any information about these variables that we can use to write either x or y in terms of the other? And so take one of them and get them out of our face. Well, we haven't used the 180 yards business yet. So what we can say is, look, we can't work with this equation the way it is. We got too many variables. But what else do we know? Well, we know that there's 180 yards of fencing. And how is that going to be distributed? Well, that's going to become the perimeter of this rectangle. And based on our lettering and the fact that there isn't any fence along the stone wall, that perimeter will be x plus 2y. And that means that x itself is 180 minus 2y. And that means that our area can be written as 180 minus 2y times y, which is equal to negative 2y squared plus 180y. And even though it's written with y's instead of x's, we don't care about that. It's starting to look like the equation of a parabola. Now, ideally, it would look like that standard form. And again, x's versus y's doesn't matter. We just have to know which one the variable is. So maybe a little completing a square, just like we did the problem above. I'm going to factor off that negative 2. And I'm going to be very careful when I do that. I've already been not too careful because I almost wrote 180 all over again. If I'm factoring out the negative 2, I'm pulling it not from just the y squared term, but I'm also pulling it from this term. And negative 2 divided away from 180 leaves me with negative 90. Okay, so here's my expression. I'm going to do what I did above, which is make an attempt to complete the square. I'm going to get my red pen again. And completing a square, remember, take half of this number, which is now 45 or negative 45, and square it and add it in there. Now, it should be negative 45 squared, but negative 45 squared and 45 squared are the same number. And I'm just going to leave it written as 45 squared because I do not want to have to figure out what 45 squared is. Balancing the equation, I've just added in not only this 45 squared, but negative 2 times that 45 squared. So I need to subtract that negative 2 times 45 square on the outside. And then the final version of my equation, whoops, and here's the great part of this, is I didn't need to know what 45 squared was because I would just have unwrapped that expression back into y minus 45 squared altogether. There we go. And where is the vertex of this parabola? Well, the vertex of this parabola is at y equals 45. So the vertex, or the maximum, is at y equals 45. And if y is 45, how about x? Well, here, how about using this one? Here's our relationship between x and y. So if y is 45, this is 180 minus 2 times 45, 180 minus 90. And there we go. Now, how do we know that this value of y of 45, where the vertex is, provided us a maximum? Well, because this number out front is -2, which means the parabola opens upside down, which means that the vertex is the maximum, not the minimum. And now I should be good and go back and write an answer to that question by saying the rectangle should have length of 90 yards and height of 45 or something like that. But I'm kind of out of space. So we'll all be friends here and agree that it should have been done, but it won't be.